Hello everyone, and welcome back to my channel. Continuing in the mini-series on the classical chemistry experiments, today we'll be talking about the Millikan oil drop experiment, conducted by that lovely gentleman you see at the bottom right of your screen. This experiment tends to be a little tougher for some students to understand, but it's really not that complicated if you just take a little bit of time to picture and to understand what's going on here. So, just like last video, we're first going to go over what the scientists were looking to investigate. Then we'll talk about their experimental setup and the theoretical basis behind it, which unfortunately does include some math. And lastly, we'll summarize the results. So to set the stage here for the experiment, we got to understand the controversy over the nature of the electron that was going on at that time, which was fundamentally really about whether the electron was a particle with a precise amount of negative charge, or whether negative charge was a continuous property that didn't necessarily need a particle to be contained. So, on the one hand, we have the work of people like J.J. Thomson, most prominently, who actually popularized the plum pudding model of the atom that we discussed last time. So, his 1987 cathode ray tube experiment characterized what he called corpuscles, which were essentially units or packets of negative charge. And this provided some decent evidence that a distinctly negatively charged particle might exist, hinting at the later discovery by people like Millikan of the electron. On the other hand, other more traditionalist physicists and chemists still held to a slightly older view that charge might be continuous, like they believed light to be at that time in history. Of course, we now know that light can be explained both as a particle and a wave, but back then, it appeared that both light and charge had properties consistent with waves, so they were continuous. And so, to help resolve this debate, Millikan wanted to determine if negative charge was quantized into distinct particles, like the work of Thomson suggested, or whether negative charge might be continuous, like people thought light was. So, how did Millikan test this? The picture I have here below is a rough schematic of Millikan's experimental setup. While it might seem complicated, it's really not. So, starting from the top, he uses this oil atomizer, which is just like a spray bottle, essentially, to inject microscopic oil droplets into this big chamber. So this is basically one of those like olive oil spray cans, more or less. The oil droplets then would fall down because of gravity through this small opening into a second chamber that's made up of two metal plates. So the top plate, as I've indicated here, is positively charged, and the bottom plate is negatively charged, which creates an electric field between them, and that's going to be really important later. The last thing to mention here is that he's got this X-ray emitter over on the right, which is shooting X-rays through the field that hits the oil droplets, ionizing them and giving them a negative charge. So the resulting thing we'll have here is an oil droplet that's fallen through here that's given a negative charge. And the amount of negative charge is not important, just that it has a negative charge, which is given to it by this X-ray emitter. Okay, so essentially what's going on here is the droplets have two forces acting on them. There's the gravity that we talked about that's pulling them downwards, right? And that's being counteracted by an electrostatic force. And all that means, I'm sure you guys know that positive and negative things attract, and negative and negative things repel. So like charges repel, opposite charges attract. If this oil droplet is negatively charged, it's going to be attracted to the top plate and repelled away from the negative plate. So we'll have gravity pulling it down, and then this new electric force pulling it up towards that positive plate. And we can use that fact, the counteracting forces, along with a little bit of math to figure out the charge of each droplet. So let's talk about the math. First, as we just did, it's important to define each of the forces involved here. So again, we've got this gravity pulling down and the electric pulling up. And then we can use a couple of really simple equations to describe both gravity and the electric force. So the electric force is defined as the multiplication of the charge and the electric field strength, which is just a constant that Millikan would have known in his experiment. And gravitational force is the mass of the oil droplet multiplied by the gravitational acceleration, which is also a constant. So pretty simple math here. And the way we use these equations together is in the situation where the oil droplet remains suspended midair. So weird to think about, but just bear with me. If the oil droplet stays suspended in midair between these two plates, that means that the downward force of gravity must be equal to the upward electrostatic force. In that situation, the two forces will essentially cancel out, leaving the particle literally floating midair, which is kind of cool to think about. So if the two forces are equal, we can just set them equal in our equation. So we get gravitational force equals electrostatic force, which means that m times g equals q times e. And q, because remember, we're trying to find the charge of the particle here, q equals mg divided by e. So pretty simple. We know g, we know e. All we have to do is find the particle's mass or the oil droplet's mass, and we can easily calculate q. And just a quick aside here, and you can skip this bit. How do we find the droplet's mass? When Millikan is actually looking into this chamber at these droplets, he can calculate their radius or their diameter via simple microscopy, and then just apply this volume formula. So volume equals 4/3 pi times the radius cubed. So he'll get the volume from that, and then use the oil density, which will have units of grams per cubic centimeter or grams per milliliter, something like that, to get the mass from the volume. So pretty simple there. What did Millikan find? As you might expect, with your current chemistry knowledge, he found good evidence for a distinct negatively charged particle, or at the very least, he found evidence for the idea that negative charge exists in discrete units. So when they plugged in the masses of the oil droplets, they found that all of the charges they calculated, so all of those Q values they calculated, were integer multiples of around 1.6 times 10 to the minus 19th power. And the exact number is a little different, but more or less 1.6, which is the same value we have today for the charge of one electron. So super cool. To explain this, let's look at this diagram here. So let's say we've got a particle with mass m. In order to stay suspended in midair, it needs to have a negative charge of q. Let's just say, for the sake of the argument here. So if we have a particle with mass 3m, so 3 times m, it will need a charge of negative 3q to stay suspended, because the downward force of gravity is dependent on the mass, and the upward electrostatic force is dependent on the charge. So if the mass goes up, the charge has to go up in equal proportion to stay suspended. And Millikan observed particles that were just like both of these, suspended in midair. However, he was never able to observe a particle with a mass of 2.5 m, for example, or really any other fractional multiple of m that was suspended in midair. Those particles all went either up or down. Millikan's explanation for this is that charge cannot be continuous, or else this 2.5 m particle could have just had a charge of minus 2.5 q and be suspended in midair. It must be that the particle with mass 2.5 m has a charge of either negative 3q or negative 2q or negative q or some other integer multiple of q, which will cause it to either be attracted upwards, like in this case, or pulled downwards by gravity. That's all for today's video. I hope you enjoyed it. Please like and comment, subscribe, all that stuff. If you like the way I teach and are interested in some affordable one-on-one tutoring in chemistry, biology, or the MCAT, please shoot me an email or scan the QR code that's on the screen right now. And see you next time.